forwards. So now, if I wanted to apply that total energy operator on the wave function, so we can see already how our simple little Schrödinger equation indeed blows up, okay? And so now what we're dealing with for now is the one-dimensional translational motion only, so we're not building in the vibrations or the rotations just yet, and time independent, okay? So this is kind of what we call the standing wave approximation. In a more advanced class, perhaps a graduate school class or in a physics department, you would do the time-dependent Schrödinger equation. And that adds a huge degree of complication. So that's why it is very typical in a chemistry-based quantum mechanics class to look at the time-independent Schrödinger equation as your introductory to quantum mechanics. Okay? So how do we get this result? Well, I will remind you our total energy Hamiltonian operator, okay, is negative h bar squared divided by 2m, okay? Second derivative, and instead of putting a partial, I will just put ddx squared. We're just assuming this is only one dimension, okay? And then that's plus the potential energy. And for now, we haven't put any type of equation, right? We're just using the symbolic v of x, okay? So this is our kinetic. This is our potential. And because this total energy operator, this Hamiltonian, is both the kinetic operator and the potential operator, when I apply this operator through the wave function, notice here now what happens. We have the second derivative of psi of x, okay? I'll put that in a red color, okay? So we first, on the order of mathematics, would have to take the second derivative of psi of x with respect to x, okay? Then we multiply that result, so I'll say times, by negative h bar squared divided by 2m. Also, we have another operation going on, which would be to operate the potential energy operator on psi, which for now, like I said, we haven't put a specific mathematical operation in that yet. And what we would get out of this then would be the single valued, the energy of the system. And we would return the original wave function, okay? So just to walk you through why the kinetic energy operator is negative h bar squared divided by 2m. So recall from classical mechanics. And so anytime I refer to classical mechanics, you know, we're talking about Newton's laws. We're talking about describing cannonballs flying through the air, okay? So we can write the velocity of an object as a vector, okay? Which we know that's dx by dt. So that's the derivative of the position x with respect to time. We also know that momentum is mass times the velocity, okay? We know that total energy is going to be 1/2 mv squared, as well as some arbitrarily defined potential energy operator. It could be a constant, like, you know, perhaps I'm holding this object up here, and this, like, you know, this would give me the gravitational potential, which would just be a constant. Or if there was some potential energy that was changing in time or position, we would have to put that operator in place, okay? And so also recall, last time, okay, we wrote, I'm just going to write that KE, we know that that's 1/2 mv squared, but remember that we came up with this last time, that this is really momentum squared divided by 2 times mass for the kinetic energy. And that's going to be far more useful. We're going to see using kinetic energy with respect to momentum as opposed to just mass times velocity squared, okay? So now I'll remind you our potential energy operators on this previous sheet, right? Negative I times h bar times d dx, okay? So let's write that down over here. So the momentum operator, and I'm going to put this sub x because for now we're only dealing in one dimension, okay? So that sub x is just reminding us this is one dimension. So in that handout, that was written as negative I times h bar times d dx. However, this form is also acceptable. H bar divided by I, no negative sign, okay, times d dx. And I have a little Mathematica notebook open here. I want to show you something. I'm going to remind you, I'm going to be using Mathematica throughout these lectures to kind of remind us of some math that is not so straightforward. So in Mathematica, I can push escape, escape, and that gives me imaginary number I. And we know this has to be imaginary number I, because if I say I squared, let's remind ourselves what we should get. I'll put that up here. So we know that I equals the square root of negative 1. Therefore, I squared just equals negative 1. So to prove that we did that correctly in Mathematica, I squared, and there we go, there's negative 1. So I'm going to show you a rather obscure proof with imaginary numbers. I'm going to write here now 1 divided by escape, I, escape. So 1 over I is negative I. This is a weird proof. I'm not going to go through this proof. I'm just going to rely on the fact that Mathematica knows what it's talking about, okay? So that's where we can see these kind of two different forms of the momentum operator, negative I h bar d dx or h bar over I d dx. And I kind of prefer this one because I don't have to deal with a negative number at that point, okay? And so then I will also say, because look, we know that the kinetic energy is going to be momentum squared, all right? If I square the momentum operator, okay, and I'm going to square this version of it, that's going to be h bar squared over I squared. And then now that also square the derivative, so I get the second derivative, okay? And now we know that that is going to be equal to negative h bar squared times second derivative with position in x. And so now we can finally see here my kinetic energy operator, which I will, often we see the kinetic energy operator symbolized as T in some textbooks. And I don't want you guys to get too freaked out about all these different letters we're going to use. Some folks use KE, some folks use T. So I'll just try to make sure to communicate the letters. So I'm just going to call this, instead of saying KE, I'm going to write T hat, just so we recognize this is an operator we're talking about, okay? So we know that that's going to be momentum squared divided by 2 times mass. Well, we know just momentum squared is negative h bar squared times the second derivative, and then look, we've got that divided by 2 times mass. So that's where we get this equation from, the negative h bar squared divided by 2 times mass multiplied by the operation second derivative of psi of x with respect to x. Okay, so that's where that all comes from. Beautiful. I think that's what I want to say on this slide. Okay, so moving forward.